Hello, and welcome back to my sleepy journal. If you're someone who relaxes by imagining distant stars, quiet planets, and the gentle beauty of the cosmos, then you've arrived exactly where you need to be. Tonight, we'll travel far beyond the borders of our solar system. We'll drift through the vast darkness between the stars, where unfamiliar planets circle distant suns, and the impossible quietly becomes real. We'll explore worlds where metal falls like rain, planets shaped by ice and fire, and solitary giants wandering through space without any star at all. Some of what you're about to hear may sound unreal, almost like science fiction, but every detail is grounded in discovery. And if you enjoy these calm cosmic journeys, you're always welcome to like and subscribe. It helps other dreamers find their way here too. But for now, settle in. Let your body soften into stillness. Let your thoughts loosen their edges. And together, let's begin. There are planets with temperatures hotter than some stars. When we think of stars, we imagine blazing spheres of plasma, immense furnaces burning at millions of degrees. Yet, astonishingly, certain planets approach that same intensity. One such world, Kelt 9b, reaches temperatures above 7,000 degrees Fahrenheit, hotter than many red dwarf stars. This enormous gas giant orbits incredibly close to its massive blue star, completing a full revolution in just over a single day. It is tidally locked, with one hemisphere permanently facing the star, absorbing relentless radiation without pause. Its atmosphere is being stripped away, pulled into space like the glowing tail of a comet. The heat is so extreme that molecules are torn apart and even metals can vaporize into gas. It isn't merely hot, it is heat beyond comparison. These ultra-hot Jupiters challenge our assumptions about what a planet can be. They blur the line between planet and star, existing as blazing, storm-lashed infernos that may survive only briefly on cosmic timescales before fading into darkness. Some planets may be made almost entirely of diamond. It sounds like fantasy, but under certain conditions, it could be true. On exoplanets rich in carbon, especially those that formed around stars containing more carbon than oxygen, the chemistry of birth can favor carbon-heavy structures. One intriguing candidate is 55 Cancri e, a super-Earth roughly twice the size of our planet that may contain vast quantities of carbon compressed under immense pressure. Deep within its interior, that pressure could transform carbon into enormous regions of crystalline diamond. It wouldn't sparkle the way we imagine gemstones on Earth. There would be no glittering facets, no jewelry. Only darkness, crushing heat, and unimaginable density.
Still, the thought is mesmerizing. A planet forged from carbon, mountains that may conceal buried crystal, a geology so extreme it feels almost sacred. Some exoplanets orbit two suns, much like Tatooine in Star Wars. For decades, science fiction imagined twin sunsets, two stars sinking together beneath an alien horizon. Now we know such skies may truly exist. Certain exoplanets do not circle a single star the way Earth does. Instead, they orbit pairs of stars locked in mutual motion. These are known as circumbinary planets. They follow complex, graceful paths around two suns that revolve around each other. If the stars are close together, the planet may circle them both as though they were one. If the stars are farther apart, the planet might orbit just one, gently tugged and tilted by the gravity of the other. The result is a world with unusual cycles of light, shifting seasons, and overlapping shadows. These systems are rare and delicate, yet they are real.
Somewhere, a distant sky may truly glow, with two dawns and two dusks. A vision once confined to imagination, now confirmed by science. There are planets where molten glass falls from the sky. Some worlds are so alien that even their weather feels impossible. Consider HD 189733b, a gas giant larger than Jupiter that orbits so close to its star it completes a full orbit in just over 2 days. Its atmosphere burns at around 1,700 degrees Fahrenheit. Winds whip across the planet at thousands of miles per hour. Suspended in its hazy blue skies are tiny particles of silicate, the building blocks of glass. When conditions align, these particles condense and fall as rain. Not water, not ice, but molten glass, driven sideways by ferocious winds. From a distance, this planet appears almost serene, glowing in a soft blue shimmer near its star. But up close, it is a furnace of storms, beautiful, violent, and utterly uninhabitable. It reminds us that nature's creativity stretches far beyond our imagination. Other planets may be covered in oceans thousands of miles deep. Some exoplanets could be true ocean worlds, nearly entirely enveloped by water. No continents, no islands, only endless global seas. Unlike Earth's oceans, which reach only a few miles down, these waters could extend hundreds or even thousands of miles in depth. At the surface, the sea might be calm or whipped by storms, but far below, pressure would build to extraordinary extremes, forming exotic types of high-pressure ice. Not the familiar ice of winter mornings, but dense crystalline forms created under crushing weight. Beneath those layers, a rocky core might lie hidden. Some worlds could even contain liquid regions warmed by internal heat. Could life exist in such oceans? We don't yet know. But ocean planets may be more common than we once believed. Gentle, glistening spheres with no land in sight, turning quietly in darkness, far from any sun we recognize. Some planets are tidally locked, with one side forever facing their star. Not every world spins like Earth. On these planets, one hemisphere remains locked in endless daylight, while the other lies in perpetual night. Our own moon behaves this way toward Earth, always showing us the same face. Imagine that condition stretched across an entire planet. One side scorched beneath unceasing light, the other frozen in eternal darkness. Between them lies a narrow twilight band, a ring of perpetual dusk where temperatures may be balanced just enough to allow something fragile to survive. Some scientists believe that if life exists on such worlds, it might cling to that thin region of equilibrium. Fierce winds would likely roar across the boundary, strange clouds forming where hot and cold collide. These planets challenge our definitions of habitability. Life, if present, might learn to thrive in shadow, or right at the delicate edge of light. Hot Jupiters skim so close to their stars that their atmospheres begin to boil away. Picture a planet like Jupiter, immense and gaseous. Now imagine moving it dangerously close to its star. So close that a full orbit takes only days. So close that temperatures exceed 2,000 degrees. These are hot Jupiters, giant planets grazing the edges of their star's influence. Their upper atmospheres can be blown into space, streaming outward in glowing tails. Many were among the first exoplanets we discovered, because their size and tight orbits made them easier to detect. Yet they remain mysterious. How did such massive planets end up so close? Did they form there? Or were they pushed inward by gravitational forces over time? Some are slowly shrinking as their atmospheres evaporate. Others trail luminous arcs of gas like comets. They are dramatic and unstable, brief flashes of planetary fire circling distant suns. Some exoplanets are darker than charcoal. Not every planet reflects light like Earth. Some absorb nearly all of it, becoming darker than paint, darker than ash. One such world, Tres 2b, reflects less than 1% of the light that strikes it. The reason isn't fully understood. Vaporized alkali metals or unknown atmospheric compounds may trap incoming light. The result is extraordinary. A planet as black as coal, glowing faintly from its own heat, nearly invisible in reflected starlight. Even its night side is only slightly cooler than its day side. If you could somehow stand nearby, you might see only the faintest outline against the blaze of its star, a near-perfect shadow orbiting in silence, quietly absorbing the universe's light. We have found planets drifting alone without any star. Most worlds orbit suns bound tightly by gravity, but some are wanderers, free-floating planets moving through the galaxy without circling any star at all. These are known as rogue planets, and evidence suggests there may be dozens, perhaps even hundreds of billions of them scattered across the Milky Way. Some likely formed in ordinary planetary systems and were later ejected by gravitational disruptions, flung outward during chaotic early encounters. Others may have formed in isolation, like failed stars that never gathered enough mass to ignite fusion. These worlds are dark and cold, incredibly difficult to detect. But with sensitive infrared telescopes, we can sometimes glimpse their faint internal warmth. Some rogue planets might still hold residual heat deep inside, possibly maintaining subsurface oceans for billions of years. Others may be completely frozen, drifting endlessly through interstellar space. A planet without a sunrise, a sky without a sun. And still, even there, the question lingers quietly. Could something endure in such silence? Some worlds may have clouds made of rubies and sapphires. When we picture clouds, we imagine soft white vapor drifting through blue skies. But on certain scorching gas giants, temperatures rise above 2,000 degrees Fahrenheit, hot enough to vaporize minerals that would be solid rock on Earth. Aluminum oxide, iron, titanium, and even corundum, the mineral that forms rubies and sapphires, can rise as vapor into the atmosphere and condense into clouds. These mineral clouds may scatter light in strange ways, tinting the sky deep red, violet, or luminous blue. On planets like HATP 7b, shifting atmospheric patterns suggest high-altitude mineral clouds sweeping across the globe. It's difficult to imagine a world wrapped in blistering heat, storm-torn and brilliant, with clouds of liquid gemstones swirling overhead. And yet, such skies may exist. The universe is stranger and more beautiful than we once believed. There are super-Earths that might be even more habitable than Earth. Super-Earths are rocky planets larger than our world, but smaller than Neptune. They may have stronger gravity, thicker atmospheres, and potentially more stable climates. One promising example is Kepler 442b, a rocky planet located within the habitable zone of its star. It receives roughly the right amount of starlight, not too much, not too little. Its mass suggests it could retain an atmosphere and possibly liquid water. Some super-Earths might have deeper oceans, fewer violent tectonic shifts, and long-lasting surface stability. We don't yet know if any of them truly support life, but they remind us of something humbling. Earth may not be the most perfect planet,
it may simply be the one we know best. We have discovered planets that complete an orbit in only a few hours. On Earth, 1 year equals 1 orbit around the Sun. Mercury, the fastest planet in our solar system, takes 88 days. But some exoplanets move much faster. Kepler 78b, slightly larger than Earth, completes a full orbit in just 8.5 hours. It is so close to its star that its surface may be covered in molten rock. Temperatures climb into the thousands of degrees.
These ultra-short period planets are often tidally locked, with permanent day and night sides. Their stars loom enormous in the sky. Gravity pulls fiercely at their structures, and some may even be slowly tearing apart. They skim their stars like sparks flying from a flame, brief and brilliant. Other planets take centuries to complete a single orbit. At the opposite extreme are long-period exoplanets that drift in slow, majestic arcs. One example, GU Piscium b, takes roughly 1,000 years to circle its star. Its orbit stretches so far that it is barely held by gravity. We cannot wait centuries to watch such planets complete a revolution. Instead, we detect subtle motion, faint curvature in their paths, hints of something vast. On such worlds, seasons might last lifetimes. Change would unfold over generations, a slow, steady rhythm, far beyond human experience. We have discovered thousands of planets beyond our solar system. For most of history, humanity knew only one planetary system, our own. But in the 1990s, the first confirmed exoplanets were identified. Since then, missions like Kepler and TESS have revealed thousands more. Some are rocky and Earth-like. Others are massive gas giants. Some orbit tightly in days. Others wander in centuries-long journeys. And we now believe there may be hundreds of billions of planets in our galaxy alone. Perhaps more planets than stars. Worlds upon worlds, quietly circling in the dark. We may never visit them, but we can measure their shadows and listen to the subtle music of their motion. We detect planets by watching the shadows they cast. When a planet passes in front of its star from our perspective, the starlight dims ever so slightly. This is called the transit method. The change in brightness is tiny, often less than 1%. Yet from that faint flicker, we can determine the planet's size, orbit, and sometimes even hints of its atmosphere. Telescopes like Kepler and TESS have used this method to uncover thousands of distant worlds. We are watching stars blink, just slightly, to learn about planets we cannot see directly. A silhouette crossing a distant sun. Others were discovered through the gravitational wobble they cause. A planet does not simply orbit its star, it tugs on it. As the planet moves, the star shifts slightly in response. This tiny back-and-forth motion alters the star's light in measurable ways. By studying subtle changes in wavelength through spectroscopy, astronomers can detect this wobble. This is known as the radial velocity method. It was how the first exoplanets were found. We may not see the planet itself, but we can feel its presence in the movement of its star, like a dance sensed through music rather than sight. Some planets appear to have atmospheres escaping into space. On extremely hot, close-in worlds, radiation from the star heats the upper atmosphere until gases begin to drift away. These planets can form long, comet-like tails of hydrogen and helium streaming behind them. Over time, some may lose significant portions of their mass. Others might be stripped down to bare, rocky cores. Even worlds can erode. Even planets can fade. And in that slow transformation, we glimpse how stars sculpt the systems around them. We have found planets in systems with 3 or even more suns. Not every star system resembles our own quiet arrangement. Some stars are born in pairs, others in trios. A few exist in even more complex families, orbiting one another in delicate gravitational patterns. And astonishingly, planets have been discovered within these intricate systems. Imagine standing on a world where the sky is never truly dark. One sun might be rising as another sets. Shadows could stretch in different directions. Light might overlap, shimmer, or shift unpredictably across the surface.
For such a planet to survive, its orbit must be stable, balanced within the tangled gravitational pull of multiple stars. Some circle tightly around 2 stars together, like circumbinary planets. Others orbit far beyond the entire stellar cluster, tracing wide, graceful loops around a chaotic center. The lightning would be unusual, the seasons uncertain, the sky constantly in motion. And yet, these planets exist. They remind us that planetary systems can form even in places where gravity is complicated and restless. The universe finds a way to build worlds, even in crowded and dynamic environments. Some planets orbit the collapsed remains of dead stars. Stars do not live forever. When a star like our Sun reaches the end of its life, it sheds its outer layers and leaves behind a dense white dwarf. More massive stars may collapse into neutron stars or even black holes. And around some of these stellar remnants, planets continue to orbit. These are worlds circling what remains after a star has died. In some cases, they are survivors, having endured the chaos of a supernova explosion. In others, they may have formed later from the leftover debris, rising quietly from the ashes. The light from these stars is dim, distorted, or pulsing. But the planets persist. They move along silent paths through what feels like a stellar graveyard. Some are blasted by radiation. Others drift in twilight around fading embers. It is haunting and strangely beautiful. Even after a star's death, new chapters can begin. One planet even orbits its star backwards. Most planets orbit in the same direction that their star spins, formed from a single rotating disk of gas and dust. But nature does not always follow our expectations. WASP 17b is one example of a planet that orbits in the opposite direction of its star's rotation. Instead of moving with the flow, it pushes against it.
This retrograde orbit likely formed through dramatic gravitational interactions long ago. Perhaps a near collision or violent rearrangement. The planet itself is massive and bloated, orbiting close to its star every few days. Its backward motion challenges our models of planetary formation. It reminds us that the universe is flexible, chaotic, and far more inventive than any tidy theory. Some planets follow the current, others resist it. We have detected clouds on planets light years away. We cannot see these clouds directly, but we can infer their presence by studying how starlight filters through a planet's atmosphere during transit. As light passes through the thin edge of an alien world, certain wavelengths are absorbed while others scatter. This subtle fingerprint reveals gases, particles, and sometimes the existence of clouds. These clouds may not be soft and white like those on Earth. They may be made of silicates, iron, or exotic chemical compounds. Some planets appear permanently cloud-covered. Others show shifting atmospheric patterns. We cannot yet look up at these skies with our own eyes, but we can read their weather from starlight alone. Some exoplanets orbit closer to their stars than Mercury does to our Sun. Mercury already experiences intense heat and radiation. Yet many exoplanets circle even nearer to their stars, completing orbits in hours or days. Their surfaces may be molten. Their atmospheres may be stripped away by stellar winds. Some are stretched into teardrop shapes by tidal forces. Others are tidally locked, with one side forever blazing and the other frozen in darkness. These extreme planets are among the easiest to detect because of their rapid orbits. Many of the first exoplanets discovered belonged to this category. They are harsh and unstable, yet they reveal just how diverse planetary systems can be. Other worlds drift far beyond the reach of warmth. Not all planets cling close to their stars. Some orbit so far away that starlight becomes faint and distant. Their years may last centuries or millennia. Temperatures plummet, chemical reactions slow. Yet even at the outermost edges of a star's gravitational grasp, planets endure. Some may be icy giants wrapped in frozen clouds. Others may hide internal warmth beneath layers of ice. In these cold, remote regions, worlds persist quietly, turning at the edge of darkness. There may be planets with enormous ring systems. Saturn's rings are breathtaking, but they may not be the most spectacular in the universe. Some exoplanets appear to host ring systems hundreds of times larger than Saturn's. One candidate, J1407b, may possess rings so vast they could eclipse their star for extended periods. These rings might be composed of ice, dust, and rock, perhaps even the building blocks of forming moons. If such a planet were placed in our solar system, its rings would dominate the sky, stretching across the horizon. Though still under study, their existence hints at cosmic grandeur beyond anything we have witnessed up close. And still, we have only begun. The first confirmed exoplanet discovery was made in 1992. In cosmic terms, that is barely a moment ago. Since then, technology has advanced rapidly. Thousands of planets have been confirmed, and countless more await discovery. We have measured their sizes, mapped their orbits, and even begun analyzing their atmospheres. Yet we still do not know what their surfaces truly look like. We cannot yet feel their winds or hear their storms. Each new planet is a doorway, and as our tools improve, the image of the cosmos grows richer and more intricate. The galaxy is filled with worlds, and we have only just begun to knock on its doors. Some planets orbit so close that they are slowly vaporizing. For certain exoplanets, proximity to their star is not merely hot, it is destructive. Radiation and stellar winds heat their atmospheres until gases expand and escape. Long glowing tails stream behind them, like comets retreating from the light. Over time, these planets lose mass, thinning and transforming. We are watching erosion on a planetary scale. Even something as vast as a world can be worn away by the relentless energy of its star. And with every discovery, we realize something deeper. The universe does not settle into predictable patterns. It surprises us. We have found lava worlds hotter than imagination. We have found planets colder than deep space, worlds too dense, worlds too light, worlds that should not exist according to earlier models. Yet they do, and each one forces us to expand our understanding. Science grows not only through order, but through exceptions, through strange cases and quiet contradictions scattered across the galaxy. Little cosmic puzzles waiting patiently in the dark. Some exoplanets may be true water worlds with no land at all. Imagine a planet without continents, without coastlines, without even a single island breaking the surface. Only endless ocean stretching in every direction. These worlds may be covered entirely by liquid water, not shallow seas like Earth's, but oceans hundreds or even thousands of miles deep. Beneath the surface, the pressure would become immense, compressing water into exotic forms of ice,
and reshaping rock into unfamiliar structures. Some of these planets could have thick atmospheres filled with steam. Others might glow beneath hazy skies, warmed by internal heat. If life exists there, it would evolve in darkness far below the waves, shaped by chemistry and pressure rather than sunlight. We have not confirmed such a world yet, but the evidence is growing. If Earth represents one path to habitability, perhaps these deep ocean planets represent another entirely. We have discovered many mini Neptunes, small but swollen with gas. Between Earth and Neptune lies a curious class of planets we call mini Neptunes. They are larger than Earth but smaller than our ice giants, often wrapped in thick layers of hydrogen and helium. These planets may have rocky or icy cores hidden beneath vast envelopes of gas. From a distance, they resemble Neptune, but inside, they may be very different. Some could harbor deep, boiling oceans beneath their clouds. Others may have no solid surface at all. For a long time, we did not know whether planets like this even existed. Now we believe they may be among the most common types of planets in the galaxy. Strange, swollen, and still mysterious, they fill a category we once never imagined. Some planets are puffed up like balloons. Certain exoplanets are so low in density that they appear almost impossibly inflated. Huge in size, yet light in mass. One example is WASP-17b, a gas giant nearly twice the size of Jupiter, but with far less mass. Intense heat from its nearby star causes its atmosphere to expand dramatically. Radiation may break apart molecules, contributing to its strange, bloated structure. Some of these puffy planets trail faint streams of escaping gas. Others simply hover, soft and diffuse. They remind us that planets are not always rigid spheres. Sometimes they are stretched, delicate, and shaped by the light of their stars. There are exoplanets where a day can last longer than a year. On Earth, we rotate once every 24 hours and orbit the Sun once every 365 days. But on some exoplanets, especially those orbiting very close to their stars, rotation and orbit behave differently. In certain cases, the planet completes an entire orbit before it finishes one full rotation. Many of these worlds are tidally locked. One side faces the star forever. The other remains in permanent night. There are no sunrises, no sunsets, just one eternal face turned toward the light. On such a planet, time would feel unfamiliar. A year rushing past, while the same hemisphere remains fixed beneath a burning sky. Some worlds may be wrapped in thick, hazy atmospheres. We often imagine alien skies as clear and vivid, but many exoplanets may be veiled in dense layers of haze, made from complex hydrocarbons or exotic photochemical smog. On Saturn's moon Titan, we see a golden haze that obscures the surface. On distant exoplanets, similar but even stranger hazes may exist, trapping heat and scattering light. These planets might appear muted or dim from afar, but beneath the haze, storms may rage, oceans may churn, and alien landscapes may stretch unseen. The veil hides more than it reveals. We have detected winds blowing at thousands of miles per hour. Weather is not unique to Earth. On large gas giants, especially those tidally locked to their stars, temperature differences between day and night sides can drive extraordinary winds. Using spectroscopy, astronomers have measured atmospheric winds exceeding 5,000 miles per hour, fast enough to cross a continent in less than an hour. These winds shift heat across the planet, reshape cloud patterns, and move vaporized metals through the sky. Though invisible to us directly, their motion is written into the shifting light we observe from afar. Some planets may be heated from within. Not all planetary warmth comes from starlight. Tidal forces can stretch and flex a planet's interior, generating friction and internal heat. We see this effect in Jupiter's moon Io, which remains volcanically active due to tidal heating. Similar processes may occur on exoplanets orbiting close to massive stars or engaged in gravitational dances with neighboring planets. Such worlds might appear cold from space, yet hide molten interiors or subsurface oceans beneath thick ice. Heat without sunlight, motion without fire in the sky. We have discovered planets in ancient star systems. Some stars formed more than 11 billion years ago. Around a few of these ancient stars, planets still orbit.
One system, Kepler 444, contains 5 small rocky planets and is more than twice as old as our Sun. These worlds have been circling their star for billions of years longer than Earth has existed. They formed in a universe with fewer heavy elements, suggesting they may differ in composition from our planet. Could life have arisen there long before life began on Earth? We may never know, but these ancient systems remind us that planets can endure for unimaginable spans of time. Some exoplanets may have moons we have yet to find. Where there are planets, there may be moons. Yet, despite thousands of confirmed exoplanets, exomoons remain elusive. We have detected hints, subtle variations in transit timing and brightness that could indicate a moon's presence. One candidate around Kepler 1625b may even be larger than any moon in our solar system. Moons could stabilize climates, influence tides, or even harbor life in sheltered environments. Some might contain subsurface oceans like Europa. Others may be rocky and cratered, suspended in alien twilight. We have not yet confirmed one with certainty, but they are likely there, circling quietly beyond our current reach. And some planets may host entire systems of moons. Gas giants, far larger than Jupiter, could support dozens or even hundreds of satellites. A miniature solar system orbiting a single planet. Among those moons, some might lie within habitable zones, warmed by tidal forces. Not just planets, but whole families of worlds drifting together in gravitational harmony. We are only beginning to understand the scale of what may exist. And with each discovery, the cosmos grows wider, deeper, and more filled with possibility. Some exoplanets might support life, but not life as we know it. When we imagine living worlds, we tend to picture blue oceans, breathable air, and gentle sunlight. But life may not require those exact conditions. On distant planets, biology could arise in environments wildly different from Earth's. There could be organisms drifting in acidic clouds, or microbial ecosystems thriving beneath thick shells of ice. Life might persist in high-pressure atmospheres rich in methane, or in oceans sealed away from starlight for billions of years. On Earth, extremophiles already survive in boiling acid pools, deep underground caves, and near volcanic vents where sunlight never reaches. So it is not unreasonable to imagine that alien life could be stranger still. Not forests or animals, but networks of microscopic colonies. Not oxygen breathers, but chemistry driven by entirely different reactions. If such life exists, it may leave only subtle clues, slight chemical imbalances in the atmosphere, faint spectral signatures carried across light years of space. We may never see these beings directly, but one day we might detect the quiet fingerprint of something alive. We've found planets that sit right on the edge between planet and star. There exists a boundary in mass where a planet becomes something else entirely. Some enormous exoplanets, often called superjupiters or brown dwarfs, blur that line. These objects are massive enough to fuse small amounts of deuterium in their cores, but not massive enough to sustain the continuous hydrogen fusion that powers true stars. They glow faintly from residual heat left over from formation. Some emit infrared radiation, warm embers in the darkness. An object like HD 100546b may straddle this boundary. Astronomers still debate exactly where the cutoff lies. How heavy can a planet be before it becomes a failed star? These in-between worlds remind us that categories in space are rarely sharp. The cosmos does not always draw clear lines. It blends, it shifts, it creates transitions rather than borders. Some worlds lie just at the edge of the habitable zone. The habitable zone, sometimes called the Goldilocks zone, is the region around a star where temperatures may allow liquid water to exist. But many planets orbit near the very edge of that zone, where conditions are uncertain. If a planet drifts too far from its star, water freezes. Too close, and it boils away. Yet at the margins, other factors come into play. A thick atmosphere could trap warmth. High cloud cover might reflect light and keep a planet cool. Eccentric orbits could cause dramatic climate swings. On such a world, one hemisphere might be temperate, while the other remains harsh. Life, if present, might survive only in protected niches beneath ice or within deep caves. These edge worlds are neither fully comfortable nor entirely barren. They are places of tension and delicate balance. We are learning to study the chemistry of alien atmospheres. Not long ago, analyzing the air of a planet light years away seemed impossible. Today, with instruments like the James Webb Space Telescope, we are beginning to do exactly that. When a planet passes in front of its star, some starlight filters through its atmosphere. That light carries faint spectral lines, fingerprints of molecules present in the air. By splitting the light into its component colors, astronomers can detect water vapor, carbon dioxide, methane, and other gases. From these clues, we infer temperature, pressure, and even cloud layers. In the future, we may detect biosignatures, chemical patterns that hint at life's influence. It is as though we are reading distant skies through coded messages written in light. Some exoplanets may have seasons that last decades or longer. On Earth, our seasons arise from a gentle axial tilt. But on distant planets, more extreme tilts or elongated orbits can produce dramatic changes. A planet might spend decades warming as it approaches its star, then centuries cooling as it drifts outward. Summers could last a lifetime. Winters might freeze entire generations. Life, if it exists, would adapt to rhythms far slower or more chaotic than our own calendar. Some worlds may live in permanent twilight. On tidally locked planets, a narrow band known as the terminator divides day and night. Along this ring of perpetual dusk, light never fully fades, and darkness never fully falls. In that twilight zone, temperatures may be moderate, winds may circulate gently. If life has found a foothold on such a world, it might cling to that narrow ribbon of balance. A horizon where the star forever rests at the edge of the sky, never rising higher, never setting completely. We've discovered planets locked in orbital resonance. In some systems, planets move in synchronized patterns, their orbital periods aligned in precise ratios. One planet might complete 2 orbits for every 3 of its neighbor. This gravitational harmony prevents collisions and stabilizes the system. We observe similar resonances among Jupiter's moons. In systems like TRAPPIST-1, chains of planets move together in elegant coordination, like notes in a cosmic symphony. Yet, not all systems are stable. Some appear fragile, with orbits that may unravel over millions of years. Planets may eventually be ejected or collide. What we see today may be only a temporary arrangement in a long story of motion and change. Some exoplanets have highly tilted or even perpendicular orbits. While most planets orbit near the equatorial plane of their star, others follow sharply inclined paths. These tilts may result from gravitational encounters or ancient collisions. Such dramatic histories leave clues in orbital angles and rotational shifts. A planet's tilt is like a scar, a reminder that its past may have been turbulent.
Some planets spin backward compared to their orbit. Retrograde rotation means a planet rotates opposite the direction it travels around its star. This unusual motion likely results from violent interactions long ago. On such a world, the sun would rise in the opposite direction. Weather patterns would swirl differently. The rhythm of day and night would feel subtly unfamiliar.
We have measured winds across entire alien worlds. Using precise techniques, astronomers detect Doppler shifts in atmospheric gases, revealing wind speeds of thousands of miles per hour. These winds redistribute heat from scorching day sides to frozen night sides. They shape climates, stir clouds, and sculpt weather patterns we can only imagine. Though we cannot feel those winds, we see their imprint in shifting light. Some exoplanets are bombarded by powerful stellar flares. Young red dwarf stars often unleash intense bursts of radiation. Planets orbiting close to such stars may endure repeated blasts of ultraviolet and X-ray energy. Without strong magnetic fields, their atmospheres could be stripped away over time. Habitability depends not only on distance from a star, but also on the star's temperament. Others orbit calm, long-lived red dwarfs. Some red dwarfs burn steadily for trillions of years. Around them, planets may enjoy stable warmth for spans far longer than Earth's history. In these quiet systems, life, if it arises, could have immense time to evolve. The star glows gently, and the planet turns beneath its steady crimson light. Some worlds may glow with constant auroras. Charged particles interacting with magnetic fields can produce brilliant curtains of light. On exoplanets orbiting active stars, auroras might stretch across entire hemispheres, glowing continuously. On gas giants with enormous magnetic fields, these luminous arcs could shimmer visibly from space. Skies alive, not just with air and clouds, but with charged particles dancing in electric color. And still, we have only begun to explore the diversity of worlds beyond our own. We have detected hints of clouds made from vaporized rock. On some of the hottest exoplanets ever discovered, temperatures climb so high that stone itself can turn to vapor. Silicates, aluminum compounds, and other rocky materials rise into the atmosphere as gas. As they cool, they condense into mineral clouds and tiny suspended particles. Through spectroscopy, astronomers have observed light patterns that suggest the presence of these exotic clouds. They may create hazy skies tinted yellow, gray, or even deep crimson. On certain worlds, the upper atmosphere could be filled with sand-like grains carried by supersonic winds. These are not soft, water-based clouds drifting gently overhead. They are forged from heat and pressure. Weather systems built from ground-down rock suspended high above the surface. On such planets, the sky itself is made of stone, lifted and scattered by extreme conditions. Some planets may be slowly spiraling into their stars. Orbits are not always eternal. For certain close-in exoplanets, tidal forces and gravitational interactions gradually pull them inward. bit by bit, their orbital distance shrinks. Astronomers have measured subtle changes in orbital periods, fractions of a second shortening over time. These small shifts suggest that some planets are slowly descending toward their stars. The end may lie thousands, millions, or even billions of years in the future. But eventually, such worlds could be consumed in brilliant flares of light. They continue circling for now, unaware of their fate, while gravity quietly tightens its hold. Other planets are flung outward into interstellar space. In the chaotic early days of planetary systems, giant planets can interact violently. A close gravitational encounter may accelerate one world enough to eject it entirely. These expelled planets become rogues, drifting alone between the stars. They emit no light of their own and orbit nothing. Yet infrared telescopes have detected several candidates, massive worlds wandering the dark. Some may be Jupiter-sized. Others could resemble Earth, but frozen solid without the warmth of a star. Despite the cold, internal radioactive decay might still generate heat. Subsurface oceans could exist beneath thick ice shells. These rogue planets are cosmic exiles, unbound, solitary, yet still worlds in every meaningful sense. There are planets with enormous, elongated orbits stretching across entire systems. While many planets follow relatively circular paths, some exoplanets trace highly elliptical orbits. They may swing close to their star in brief periods of intense heat, then travel far outward into darkness for decades or centuries. At their farthest point, starlight becomes faint and distant. At their closest, they race past their star in dramatic arcs. Such orbits may have formed through planetary migration or ancient gravitational disruptions. These wide, stretched paths remind us that planetary motion is not always simple or symmetrical. Some planets exist within true Goldilocks zones, where conditions may allow liquid water to persist. Earth lies within such a region around the Sun. Increasingly, astronomers have identified exoplanets orbiting at distances that place them within similar zones around their own stars. But location alone does not guarantee habitability. Atmospheric composition, magnetic fields, rotation, and surface chemistry all matter. Even so, these planets represent some of our most compelling candidates in the search for life. We have also identified temperate worlds with estimated surface temperatures comparable to Earth's. Planets like Kepler 442b and TOI 700d orbit within ranges that suggest moderate climates. We do not yet know what their surfaces look like. They may have oceans, deserts, or thick cloud layers. But their temperatures hint at the possibility of water and stable environments. The idea that somewhere beneath an alien sky, rain might fall and winds might drift gently across a distant sea is both humbling and extraordinary. Some exoplanets may experience entirely alien forms of weather. Weather depends on chemistry and atmospheric physics. On other worlds, clouds could be made of molten metal. Rain might fall as liquid glass or methane. Winds could reach tens of thousands of miles per hour. Lightning might flash through vaporized rock. Storms could last for centuries, circling the planet without pause. These climates are not variations of Earth's. They are weather systems shaped by unfamiliar chemistry and extreme forces. Beautiful, terrifying, and unlike anything we experience here. Other worlds may host cryovolcanoes and hidden subsurface oceans. Not all volcanic activity involves molten rock. On icy planets, cryovolcanoes can erupt with slushy mixtures of water, ammonia, or methane. We observe similar activity on moons like Enceladus and Triton in our own solar system. It is reasonable to imagine such processes occurring on distant exoplanets. Beneath frozen crusts, internal heat could sustain vast underground oceans for billions of years. These hidden seas may contain complex chemistry, perhaps even life. The surface may appear still and frozen, but deep below, motion continues quietly. Some planets orbit in the quiet outer regions of the galaxy. Far from the crowded spiral arms and the galactic center, stars drift more peacefully. Planets in these regions may enjoy stable orbits for immense spans of time. There are fewer nearby stellar encounters to disrupt them. Radiation levels are lower. These galactic suburbs may provide long-term stability, offering life, if it arises, time to evolve undisturbed. In contrast, other planetary systems reside in crowded star fields. In dense clusters and near the galactic bulge, stars pass close to one another more frequently. Gravitational nudges can alter planetary orbits. Nearby supernovae may flood systems with radiation. In such environments, planets must endure constant dynamism. And yet, even in these chaotic neighborhoods, worlds survive. They circle their stars like dancers in a crowded ballroom of fire and light. We've discovered planets orbiting pulsars. Pulsars are neutron stars, the dense remnants of massive stars that exploded in supernovae. They spin rapidly, emitting beams of radiation like cosmic lighthouses. The first confirmed exoplanets ever discovered were found orbiting a pulsar known as PSRB 1257+12. These planets circle a star long dead, illuminated not by fusion, but by the steady pulse of radiation. Their origins remain debated. They may be survivors of the original system or formed later from fallback debris. Either way, they are extraordinary. Planets orbiting the remnants of stellar death. Some planets may have survived nearby supernova explosions. When a star in a binary system explodes, its companion star and planets may remain. They would endure intense radiation and shock waves. Astronomers have found heavy elements in the atmospheres of certain white dwarfs, suggesting that planetary material once orbited them and may still do so.
If any world remained intact after such an explosion, it would carry scars of that violent past. There are planets with atmospheres rich in exotic gases. Some exoplanets have atmospheres dominated by hydrogen and helium. Others contain methane, carbon monoxide, sulfur compounds, or even titanium oxide. These gases influence temperature, cloud formation, and reflected light. Some atmospheres are transparent and hot. Others are thick and murky. Air on these worlds is not always gentle or breathable. Sometimes it is metallic. Sometimes it burns. Some planets may be rich in carbon or poor in oxygen. Carbon-rich planets could host mountains of graphite or even diamond. Their skies might hold methane instead of water vapor. Conversely, oxygen-poor planets might have iron-rich surfaces and unfamiliar mineral chemistry. Life, if present, would operate under different elemental rules. And now, we are just beginning to search for biosignatures. A biosignature is any detectable chemical pattern that suggests life's presence. On Earth, oxygen and methane coexist in ways that require biological replenishment.
Astronomers are scanning exoplanet atmospheres for similar imbalances. It is delicate work. Many non-biological processes can mimic these signals. But with each new observation, we grow closer to answering one of humanity's deepest questions. Are we alone? Some exoplanets may be shrouded in global dust storms. On certain dry and barren worlds, fine particles may remain suspended in the atmosphere for years. Winds sweep across desolate landscapes, lifting dust into endless circulation. Skies turn copper or brown. Sunlight fades behind a constant haze. These storms influence temperature and chemistry. They may define the planet's entire climate. Any life present would need to adapt not to rain, but to perpetual dust. Other planets reflect extraordinary amounts of light. Some worlds gleam brightly due to reflective clouds or icy surfaces. Kepler 7b may be covered in highly reflective silicate clouds. Certain exoplanets exhibit albedos so high they appear luminous even from great distances. These planets shine with borrowed light. They do not generate their own brilliance. They echo it. Some planetary systems resemble scaled-up versions of our own solar system. Rocky planets near the star, gas giants farther out, icy belts at the edges. These familiar patterns suggest that some principles of planetary formation may be universal. Gravity shapes dust and gas into recognizable architectures. But many systems break every rule we once assumed. Giant planets orbit closer than Mercury. Worlds follow tilted or retrograde paths. Planets migrate from their birthplaces. The more we observe, the clearer it becomes. The universe does not adhere to a single blueprint. It improvises. It experiments. It creates variation after variation. And with each new world discovered, our sense of possibility expands. We are building telescopes designed to see these distant worlds directly. For decades, most exoplanets were discovered indirectly, through shadows and stellar wobbles. We inferred their presence from dimming light or subtle shifts in spectra. But now, astronomy is entering a new era. Engineers and scientists are developing instruments capable of blocking out a star's overwhelming glare in order to capture the faint light of an orbiting planet. Devices called coronagraphs can suppress starlight within telescopes, while proposed star shades, massive, precisely shaped structures flying in formation with space telescopes, could create artificial eclipses in space. The goal is simple and extraordinary: to see an exoplanet not as a signal, but as a tiny point of light beside its star. From that faint dot, we could analyze reflected light, study atmospheric composition, and perhaps even detect seasonal changes. Future missions like the Nancy Grace Roman Space Telescope, LUVOIR, or HabEx aim to turn distant worlds into visible places. Soon, exoplanets may no longer be just data. They may become images. And in fact, it has already begun. Astronomers have directly imaged a handful of massive gas giants orbiting far from their stars. These photographs are not detailed. They do not show oceans or continents. They appear as faint, blurry specks beside bright stars. Yet they are real images of other worlds. Systems like HR 8799 have revealed multiple gas giants captured in direct observation, glowing softly in infrared light as they cool from their formation. Over years, astronomers have even tracked their motion, watching them slowly orbit their star. These early images are crude by comparison to what we hope to achieve, but they mark a turning point in human history. For the first time, we've seen the light of planets beyond our solar system. A blur, yes, but a beginning. The search for life almost always leads us back to exoplanets. When we imagine life beyond Earth, we imagine a world, a place with surface, sky, chemistry, and time. That is why exoplanets are central to one of humanity's greatest questions. We search for planets within habitable zones. We scan their atmospheres for oxygen, methane, ozone, and other potential biosignatures. We study their stars for stability and radiation patterns. Every promising candidate ignites discussion and hope. Could this one hold water? Could that one support microbial life? Could somewhere beneath a distant sun, biology have found a way? Even the faintest spectral signal can send ripples through the scientific community. Because if life exists elsewhere, it will likely be on a planet, a world that has quietly orbited its star for billions of years, unnoticed until now. Every new discovery reminds us how strange and inventive the universe truly is. We once expected planetary systems to resemble our own. Rocky inner worlds, gas giants farther out, orderly and predictable. Instead, we found lava planets glowing red hot, rogue planets drifting alone.
gas giants skimming the surfaces of their stars, systems packed tightly with multiple worlds in delicate resonance. We found planets orbiting dead stars, planets with molten glass rain, planets with skies dark as coal. Each new discovery reshapes our imagination. The universe is not just vast, it is creative. And the thousands of exoplanets we have already cataloged likely represent only a small fraction of what exists. There may be more planets than stars in the Milky Way. For centuries, planets were thought to be rare companions to stars. But modern observations suggest otherwise. Most stars likely host at least one planet. Many host several. When we multiply that by the hundreds of billions of stars in our galaxy, the numbers become staggering. Hundreds of billions of worlds, some massive, some small, some scorching hot, some frozen in eternal night. Planetary systems are not rare exceptions, they are common. The galaxy is not just a sea of stars, it is a garden of worlds. And somewhere among those countless planets, there may be one very much like Earth.
We do not know where it is. We do not know what it looks like. But statistically, it is likely that rocky, temperate planets exist in large numbers. Perhaps one orbits a quiet red dwarf star. Perhaps another circles a sun much like our own. It may have oceans and continents, storms and seasons. It may harbor life in forms familiar or utterly alien. Maybe it is young, just beginning to cool. Maybe it is ancient, its civilizations risen and fallen long before Earth formed. We have not found such a twin yet, but we are searching. Every telescope launched, every spectrum analyzed, every new exoplanet cataloged brings us closer. And the day we confirm a true Earth-like world with clear signs of life will change humanity forever. It will remind us that we are not alone in this vast, quiet darkness, that Earth is not an isolated miracle, but part of a greater cosmic story. And now, our journey begins to slow. Tonight, we have traveled far beyond the familiar warmth of our sun. We have drifted past burning worlds and frozen giants, through clouds of vaporized metal and oceans hidden beneath ice. We have imagined planets orbiting multiple suns, planets cast out into interstellar night, planets surviving stellar explosions and circling the remnants of dead stars. Through it all, one truth remains steady. The universe is not empty. It is filled with places. Places with gravity and atmosphere. Places with history and possibility. Each exoplanet we have considered, whether firmly confirmed or still under study, is a real world in the cosmic ocean. A sphere of rock or gas turning quietly around its star. And while you rest here, safe and still, those worlds continue their motion. Stars are shining, planets are rotating. Somewhere, under a distant sky, night has fallen. Somewhere else, a dawn is breaking across alien clouds. If your eyelids are growing heavy now, if your breathing has slowed into a gentle rhythm, you do not need to return from this journey. You are already part of the sane universe, already orbiting your own star, already home among the galaxies. Thank you for traveling through the cosmos tonight. If this quiet exploration helped you rest, you are always welcome to return. There will always be more wonders waiting, more discoveries, more distant worlds turning silently in the dark. But for now, let yourself drift. The planets will keep orbiting. The stars will continue to burn. The universe will remain vast and patient. Good night.